Okay, this is part two of the Philosophy of Time series. We're going to discuss Einstein. We're going to discuss more of the history of the science and philosophy of time. It's going to be a little bit eclectic, but the idea is that Albert Einstein reinvigorated a discussion of the philosophy of time, and that's why it's relevant to our series. And I think you can't have a philosophy of time series without discussing a little bit about Einstein. Right below here, I've linked to Jason Zari because he's been a great help with this series. This particular video, I've been self-sufficient, but some of the other stuff, I've definitely relied on him and his philosophy background for help. Just a brief overview of what we're going to be doing this series. I'm going to be doing something on idealism. I'm going to be doing something on presentism and eternalism. And I'm going to try to get to something on that's going to be interesting. It's going to be on time and the autistic spectrum. And I hope that that's an interesting one for you. So watch out for that one. Okay, mathematics and time. Now, the story of the history of using mathematics to describe time really began with the early modern period, with Descartes, with Newton in particular, with the development of modern physics. Why don't I credit the Greeks with that? Well, there's one important reason. The Greeks had, for one thing, most ancient peoples had a very cyclical notion of time. But for another thing, the Greeks had an idea of the mathematical realm of forms that was something separate from the physical world. I'm thinking particularly of the Platonists. The pre-Socratics, again, there were different Greek philosophies. You can't necessarily type them all. You have the pre-Socratics, the Socratics, the later Hellenistic schools. But by and large, a unifying factor here would be that the Greeks tended to hold to the idea of mathematics as a kind of sublime, timeless reality. And if you think about it, there's a point to what they were saying. There is a kind of irony in using mathematics to measure or to describe time, because mathematics itself, in a sense, is timeless. And that is somewhat, maybe not paradoxical, but it is somewhat ironic. Mathematicians, since the discovery of irrational and transcendental numbers, like, let's say, e and pi, mathematicians have tended to downplay the idea of a Pythagorean or a kind of transcendental realm of forms. But note this equation here, one that is considered by mathematicians to be very beautiful. And this is e to the power of I times pi plus 1 equals 0. And the reason mathematicians consider it to be very beautiful is because, again, we have e, I, pi, 1, and 0 mentioned. Here I went ahead and proved it for you. If you can freeze frame that and look at it later if you want. Mathematicians consider it very beautiful because it incorporates common recurring numbers in mathematics. E, which would be your natural logs, I, your square root of -1, pi, which describes a circle, the ratio involving a circle. Now that's a big thing for Greeks and Pythagorean circles. 1 and 0 have a kind of numinous reality to them because, in a sense, 1 and 0 are very primal numbers. They're among the first numbers that we learn, and they can symbolize, like, with computers, you notice they can symbolize on or off. So in some sense, this is seen as a very beautiful equation, but it is in a way kind of almost the modern day equivalent of Pythagoreanism, albeit with irrational numbers. So in a way, we still live in a Pythagorean universe, even though we don't technically live in their particular concept of a mathematical universe. But mathematicians today still do live in a Pythagorean universe, but with an irony, and that is, mathematicians, unlike the Pythagoreans and unlike maybe the ancient Greeks, are even more adamant about the idea of bringing equations into material reality. That the modern period, in a sense, was born with the full faith that the material reality could be described mathematically. And so you had Descartes, you had Galileo, you had Kepler. Kepler was big on the idea that numbers had a kind of mystical reality to them, like the Pythagoreans, but also the idea with Kepler is that numbers would describe the orbits of the planets. Now, I had a lot of ideas about that were pre-modern, mind you. But they were modern, for instance, numerology and a lot of occult ideas, but so did Newton. So did a lot of the early modern scientists, but they were very, very modern in the sense that they applied the idea of measurement to units of space-time. There has always, in the classical physics period until the arising of Einstein, Einstein the Great with the cape on, you have a kind of division in how space-time was considered in terms of its ultimate reality. Two schools of thought. Both schools believed that you could measure space-time using measurements and units. And it's not that the ancients didn't have that concept. They did, but it really was the moderns who really developed that in full force. One school of thought would be the Newtonian school of thought, which is that there is absolute space and absolute time. And that there is something called space-time that exists, and that forces operate through space-time. Matter moves through space-time. Energy is something in space-time. The other school of thought would be more like Leibniz. Now, Leibniz believed that space and time, particularly space, would be established through, I'm not sure about time, but space would be established through relationships. I'm not fully informed about Leibniz's philosophy of time, but I know that my suspicion is he probably would tend towards a relational understanding of time too. I could be wrong on that. But definitely he had a relational understanding of space, where if I were to take the entire universe and move it over 5 feet, that wouldn't mean anything. Because it's still the universe. All the objects are still arranged in the same way. Whereas for Newton, that would indeed mean something, and that would indeed be something important. Now, Ernst Mach revived the Leibnizian understanding of space-time as something relational in the mid-19th century, while the mainstay of physicists tended to believe in the idea of absolute space-time. Ernst Mach is said to be a forerunner of Einstein. That could very well be, I don't know, because the problem is Einstein actually did believe in space-time as something real. He believed in it. He, in a sense, unified the two schools of thought. So, in a way, Ernst Mach was a forerunner of Einstein. In a way, you would also have to point out that certain mathematicians like Gauss and Riemann, who constructed alternative models of geometry without Euclid's fifth postulate, in other words, geometry on the surface of a sphere, or that you would have geometry in curved space that would be consistent mathematically, those were also forerunners of Einstein. James Clerk Maxwell, in discovering the speed of light as a constant, was a forerunner of Einstein, although he didn't relate that to space and time. You have the Michelson-Morley experiments. Yeah, Einstein had a lot of material to build from, but it was Einstein who really made the intuitive leap that unified the absolute understanding of space-time with the relational understanding of space-time to give us the curved understanding of space-time, where it's both absolute in one sense, that would be the speed of light as a scalar, but everything else would be considered to be relative. In other words, frame of reference dependent, a kind of neo-Galileanism, where you have the frame of reference defining reality for us, except for one thing, and that's the speed of light. Einstein did another thing, though, that does raise questions on the philosophy of time. Yes, the speed of light is a constant. Yes, time dilation, length contraction, the curvy space-time fabric that you might see in some of those other flashy videos that a lot of people spend a lot of time on, with the black hole and the swirling object going in. I'm sure you'll thumb those videos up, no problem. Sorry about this one. This one's me talking to you. But I will leave you with one interesting thing. And that is, Einstein did reopen the question of the philosophy of time by asking the question about sequences. And that is, those of you familiar with the moving train, okay, and you have a moving train and then you have one person in the back of the train throwing an object to the front and another person in the front of the train throwing an object to the back. I don't have time to get into the specifics of that. You can catch other videos on that. But you can set it up such that if that train's moving through space near the speed of light, you might see an effect before a cause. That can be set up that way. Usually they use the bullets firing, but we're a family channel, so we'll just have beanbags, okay? And so if you can see the effect before the cause, it raises questions about our perception of causality that have interesting ramifications for the philosophy of time. Now, you can argue causality is not violated. I understand that, but it still raises questions that we're going to get into in the next video when we talk about idealism and time. Stay tuned.